Hi everyone, I'm Racchetti, and I will talk you about my research activities on the first year of my PhD. So the research activities carried out this year were mainly on the cyber-physical system. It is a second area of the main topic. However, it is important as it is the intersection of the physical and the cyber, which means it is not enough to partially understand the meaning of the physical components and the cyber components, but we also must understand their intersection, interactions. Thank you. Sorry. So there have been an enormous scientific and industrial interest in this area because it is closely tied to robotics, manufacturing, sensor networks, avionics, automotive, and so on. Here we have three examples. The first one is the first two are MIT projects. The first one is Cartel for traffic mitigation. The second is distributed robotics gardening, and the third is smart factories. I think everyone have heard something about smart factory during a conference. So why it is so important? There has been a lot of interest, and this highlighted some challenge. The first one is there is not any standard tool and any standard methodologies because they have to handle the physical and the computational interaction. Secondly, there are programming issues because the hardware is not object-oriented as the software. And then there are real-time and scheduling performance issues. Here we got two references. So for the first year, we focused on the methodologies challenge. Treat the physical and the computational interaction can be really complex. In fact, the engineers must take into account the dynamics of the physical process and those of the computational and the networking. So we try to face this complexity, proposing the modular machine development, which functionally decompose the system into mechatronic modules. Each of these mechatronic modules is composed by a physical part and a computational part. This decomposition is made that each module can be tested alone. And so these modules can be collected and tested until the whole system is built and tested. However, there is a problem. The identification and treatment of certain working conditions and interactions is possible only on a working machine. And so there is the need of a platform while testing and designing the development and during the development. So we used a technique that is called Hardware-in-the-loop. Hardware-in-the-loop is a technique that connects the real computational part with a simulation of the physical parts. And it is done through several phases, from the system analysis until the final system validation and verification. So we developed an Hardware-in-the-loop with our modular machine development framework in a collaboration with a manufacturing enterprise. And here we have a scheme. The computational part is run on a PLC Siemens, and then the simulation part is run on a host machine. We used MATLAB for a rapid prototyping of the model and for the simulation, and then we also made a driver in order to allow us to let the computational part communicate with the simulated physical part. So some preliminary results. The plots show how qualitatively the behavior of the module of the simulation is well captured. Qualitatively, the real module is well captured by the simulated module. And we also presented this on a paper presented in a conference this year. So in conclusion, we proposed a new design methodology. We applied this methodology to a real-world system, but we've also found some limitation, for example, on the programming, as I said in the challenges. And so for the perspective, we would like to focus on the programming challenges. We also would like to see if it is possible some hardware abstraction mechanism. And lastly, we would like to do some testing pattern framework. So I finish. I was really speedy, maybe. Thank you for your attention.